Hello everyone, I am Yufeng Zhang. Today I will be presenting this research entitled Shared Locker System Design and Truck Routing for the Last Mile Delivery Problem. This is a joint work with my advisor, Dr. Ali Rezakani. As you may know, business-to-customer boosted e-commerce sales. Even though there are many conveniences brought by the e-commerce, they also brought some challenges to our logistic system and urban transportation network. So here I have some numbers to show you the big challenge that we are facing. Last year, around the world, there are more than 16 billion packages delivered. In the UK, the heavy good vehicle has increased by 70%, and the 30% of the vehicle miles traveled are actually related to package delivery and pickup. Because of the inefficiency of the last mile delivery, the total market loss was estimated to be 1.1 billion USD, which is about 1% of the market opportunity. The inefficiency of the last mile problem really comes from the high cost associated with home deliveries. In 2015, a UPS study shows that the home delivery is still the most preferred delivery mode, even though they are always associated with high operational cost. But more and more cities and logistic companies are inventing in novel delivery modes such as collection and delivery points, CDPs, shared lockers, SLs, delivery with robots or drones. These are all becoming more and more popular. Specifically for the shared lockers, it was found in the literature the shared lockers can save about 55% to 60% of the cost compared with the attended home deliveries. So now I can formally describe our problem. We are given a set of points of deliveries or customer demand sites and the road network and also the candidate shared locker locations. There are three decisions that we need to make. The first decision is optimal locations of shared locker facilities. And then after this decision, we need to determine the optimal delivery truck routes that can be either dedicated to customers to share lockers or blended to visit both customers and share lockers. And last decision we need to determine is the optimal assignment of customer to share lockers for those customers that are not directly visited by the delivery trucks. The overall goal is to minimize the total system cost. Here comes the mathematical models. The first thing I want to show you is the objective function. In this objective function, we actually introduced a parameter called customer pickup trip cost parameter, gamma, here. It is used to represent the cost a customer pickup trip induce. So in this objective function, we are trying to minimize delivery trucks operational costs, that is by term 1 and 2, and customers pickup costs, which is computed by term 3, and also the capital cost for setting up shared lockers, which is presented in term 4. So now we can present the first model, which is the vehicle flow formulation. The first constraint here enforces that each customer has to be visited exactly once. And notice that we don't have a degree constraint for the shared locker because a shared locker may or may not be visited depending on whether it is needed in the system. The second to the fourth constraint are flow conservation constraints, which basically make sure that the tours of the delivery trucks are continuous. The fifth constraint is the vehicle capacity constraint. which makes sure that the number of packages a truck carries does not exceed its capacity. And the last three constraint on the left panel is the assignment constraint, which determines whether a customer should be assigned to a shared locker. On the right, the first two constraints are subtour elimination constraint. We actually made some adaptation to these two constraints because we have additional facility, which is a shared locker that has to be treated specially. So these two constraints are those subtour elimination constraints adapted to our problem. The third constraint is the shared locker capacity constraint, making sure that the packages delivered to a shared locker does not exceed its capacity. Here is a summary of all these constraints in the vehicle flow formulation. This is a closer look at the vehicle flow formulation. If you notice that our routing variables x has three indices, ij and a index for vehicle v. So the result of this is that we may end up with a very big problem because for every xij we need to make n copies of them, and n is the number of vehicles in the problem. That may result in a very large problem. So we want to consider some improvement to the vehicle flow formulation. This is where the MTC-based model comes into play. The first assumption we need to make is the fleet is homogeneous. This is a natural idea because we want to get rid of the vehicle index V, but that also comes with some shortcoming. Because we cannot model vehicle-specific characteristic, we need to assume same capacity and same unit operational cost. The second assumption is that the task of visiting a shared locker facility cannot be split. This is needed because later we'll need to use this assumption to set up labels of customers, which is going to be introduced in the next slide. So this is a complete constraint set for the MTC-based formulation. Similar to the other formulation, we have the constraint enforcing the exactly once visit for the customer. We have flow conservation constraint, shared locker capacity constraint, assignment constraint, and these are the label setting constraint that I just introduced, and the rest is definitions of variables. These are the here comes the computational results. First, I want to introduce the test network and the parameter settings. We have three test networks, and the first two are from the VRP community that are the common instances used by VRP researchers. The last network is from the downtown Minneapolis network, which has much more demand sides. There are 12 candidate shared locker facilities and 2 delivery trucks. The parameter we use in these experiments are delivery vehicle operational cost, which is $3 per mile. Capital cost for shared lockers is $300 per unit, and we also assume 5-year amortization period. The customer pickup cost parameter ranges from 0.5 to 1.0 because we don't have a perfect information about this cost. On this slide, I am showing you the network 3, the Minneapolis downtown network. On the left is the street map of the study area, and on the right is the sketch of the network. First, I want to emphasize that these customers and shared lockers are selected at the intersections of the road network. The green points represent a shared locker facility, and the black points represent the customer demand sides or PODs. And also I want to point out that there are many one-way streets in this network. For example, this is a one-way street, and we have this one-way street. So there are restrictions on the directions of the traffic flow on this network. So the first set of the computational results are comparing between the two models. You can see here the computational time took for each problem instance. The conclusion we can draw is that the MTZ-based formulation significantly reduced the computational time. It took no more than 40 minutes to solve a MTZ-based formulation, but for the same problem, the vehicle flow model can easily take dozens of hours or even days to solve one problem instance. In this table, we are comparing the objective values obtained by these two models, vehicle flow model and MTZ model. Generally speaking, they are very close to each other. On the third column, I calculated the improvement relative to the vehicle flow model. That is, if this number is positive, that means the MTZ model has a better solution. If it is negative, that means the vehicle flow model has a better solution. As you can see, sometimes MTZ model is better and sometimes the vehicle flow model is better, but overall their difference of the objective value is only within 2.5%, so they are very close to each other actually. On this slide, I am showing the optimal solutions graphically for the two formulations for the specific instance. On both graphs, only one shared lockers facility is selected and two customers are assigned to the selected shared locker. But for the specific case, I would say there's a little bit inefficiency here in the vehicle routings by the MTZ-based formulation. But still, their objective value are very close to each other. And this is true for all the rest of the comparisons. The second set of the computational results are on the sensitivity analysis of customer pickup cost. For each network, when we increase the customer pickup cost parameter, the objective value or the total system cost generally increases. This is not surprising because the less the customer can save, the more expensive the total cost of the system is going to be. Also, I want to show that when you have really small customer pickup costs, the system tends to open more shared lockers, which can further benefit the system. From here, I'm going to show 4 slides in a row to give you a sense of how the vehicle routes are changing, how shared lockers are changing, and how customer assignment are changing in response to the customer pickup cost parameter. So on the first figure, the customer pickup cost equal 0.5. We have 4 selected shared lockers. When the parameter is 0.6, only 2 shared lockers are selected, and there are fewer customers assigned to shared lockers. When it's 0.8, there's only 1 shared locker facility opened, and most of the customers are served by the delivery trucks directly. When the gamma parameter is 1, the problem is a traditional home delivery. None of the shared lockers is selected. All the customers are served by the delivery trucks directly. Let's pause a bit here. I want to address some problems. As you can see here, this shared locker is not assigned to any customer, but is visited from 82 to 75. The same case here and here. This is not wrong with the model. The reason for this is, first, our share locker is selected at the intersection of the road network, and second, we have one-way street, so the shortest path going from 82 to 75 has to go through this share locker. But this share locker is not open and its capital cost is not included in the optimal solution. On this slide, I'm showing a test with variable discounting factor. The motivation for this test is that we want to give more discount for those customers who are close to a specific share lockers, but also we want to penalize those assignment whose customers are very far away from a specific share lockers. So in this case, when the round trip is distance is less than 500 meters, the discounting factor is 0.3, and if the distance is greater than 2 kilometers, we set the discounting factor to 1.5. Interestingly, we see actually more opened shared locker facilities, and in this case, there are actually 7 facilities opened for the specific case, and there are definitely more customers assigned to these open shared lockers. The reason behind this is that when some of the customers can really benefit from the shared locker system, you will open those shared lockers. But now that you've already invested some money on these facilities, it will further benefit the system if more customers are using the facility, so that more customers will be assigned to a shared locker. So we say in the shared locker system, there also exists the economies of scale. When more customers are using the facility, the average cost will be reduced, and the total system cost will also be reduced. Now is the sensitivity analysis on the unit capital investment. $300 per unit is used as the base case. We also tested for other cases with both smaller capital investment and larger capital investment. The total system cost is increasing with the increase of unit capital investment. But I want to point out that when you change from $300 to $400, that's a 33% increase. The solution actually didn't change. Still, 4 share locker facilities are going to be opened. So on this end, the solution are not very sensitive to the unit capital investment. Lastly, we want to address the most important problem, that is how much benefit a system can gain from the utilization of the share locker system. So here I showed the total cost for different parameters of gamma and the relative savings relative to the traditional home deliveries. So when the gamma is 0.9 or 1, we do not have any savings with the shared lockers, but when this parameter is 0.5, we can save about 19% of the total system cost. The same graph, but with the variable unit capital investment. When this unit capital investment is at the lower bound, 200, we can save up to 28% of the total cost, and when it is at the upper bound, 400, the total saving is around 11%. So here is the conclusion part. In this research, we proposed 2 models, and through the experiments, we found that the MTZ-based formulation significantly reduced reduces the computational time for the system design problem. The solutions of the two formulations are almost identical, but the MTC-based formulation does not capture vehicle-specific characteristics. The shared locker systems exhibit economies of scale, and the total system cost with the shared locker system can be up to 19% to 28% compared with traditional home deliveries. So some directions for future work, we may consider stochastic demand cases where demand cannot be predicted perfectly, and we want to make robust decisions, especially with the locations of shared lockers. And also we want to incorporate some incentivization scheme because we want to stimulate the user's choice behavior to be aligned with the system plans them for. This is the end of the presentation, and thank everyone for your attention. I would be happy to answer your questions if you have any.